Alright, this is part 2 of our work, energy, and springs unit review. And if you notice, the title is handwritten. That's because I forgot to change the title of this. And so it used to say work and power. Now it's actually energy. Just to keep you guys informed, this is definitely the energy section of our unit review. And these are the topics we're going to cover: the gist of energy, kinetic energy, potential energy, conservation of energy, and internal energy. So this is the meat of this entire unit. And so we start with thinking back to work. Work is equal to force times distance. And if you do work, you give an object energy. And this energy is transferred from one object to the other. So if you do work, energy is transferred from you into the object you're doing work on. So that object takes in your energy, and that energy can be in different forms. If it moves, it becomes kinetic energy. If it's lifted up, it becomes potential energy. And if there's other things involved, then it's going to become different other forms. Okay? So energy comes in a variety of forms. The two main forms we're going to talk about are kinetic and potential. And we'll see those in a bit. And the other main point about energy is that it's a scalar quantity. No direction. Scalars have no direction, only magnitude. So it only matters how much energy you have, whether you have it or you don't. There's no direction attached. You can't have energy going this way or that way. It's either you have it or you don't. And so the first of the two main types we're going to talk about is kinetic energy. And kinetic energy is described in this equation as 1/2 mv squared. So if you do work on the object and the object moves, then you gave it kinetic energy. And this is the energy of movement. So if an object is moving, it has kinetic energy. If it's at rest, then not moving at all, then it has no kinetic energy. Okay? And so notice here it's dependent on both mass and velocity. So velocity is the main point. If you have velocity, if it's moving, kinetic energy exists. And so we look at each of these relationships. So notice how all of these things are in the numerator. There's nothing in the denominator besides that 1/2. That doesn't really matter. And so if mass goes up, so does kinetic energy. If velocity goes up, so does the kinetic energy as well. Okay? But the graphs here are different. And you'll see why. Look at the equation. Notice that mass has no exponent. If you increase the mass, so does the kinetic energy at the same constant rate. So it's a linear relationship. Velocity, on the other hand, has an exponent. So if you increase the velocity, the kinetic energy increases exponentially. This is the quadratic relationship. So think about if you double the speed, you quadruple the kinetic energy because you're squaring that too. If you triple it, 3 squared becomes 9. If you quadruple the speed, 4 squared becomes 16. So that's why it's a quadratic relationship versus the mass. There's no exponent. It goes up the same constant rate. Now, gravitational potential energy is a type of potential energy. So potential energy is stored energy, but gravitational potential energy is stored energy due to position in gravitational field. So potential energy is stored based on position or condition, and this particular one is based on position in a gravitational field. And if you do work to lift an object up a vertical height, then you're giving it potential energy, because this particular potential energy is equal to mgh. M is mass, g is 9.81 meters per second squared, and h is height. So it's based on height especially. Lifting it up gives it height, and so you have gravitational potential energy. And again, mass is a factor here. Mass goes up, so does the potential energy, as does height. Now, both of these share the same types of graph. Notice there are no exponents, nothing's in the denominator. Everything here is just multiplied together. So everything goes up at the same constant rate. Now, when thinking about conservation of energy, think about how if you do work on objects, you give it energy and it becomes a certain form depending on the scenario. So the same thing applies in a bunch of other scenarios where one form of energy turns into another. So all in all, the total energy stays the same. Okay? And this can be attained from work. So if you give energy to an object by doing work, you're giving it all its energy, and this energy can break down into a variety of forms, okay? That it can be used for different things. And some of the common scenarios we use are free-falling ball, pendulums, roller coasters, and slides. So if we take, for example, an object raised to 10 meters high, and you drop it down, and this is our ground level 0 meters. So as it's falling down, we take a look at where it starts out initially. It starts at the top. Now, because you are just holding it and it's at the top, it's not, if you're holding it, there's no kinetic energy because it's not moving. But the fact that it's also at a height above the ground means it has potential energy only. Now, as it's falling through the ground, it starts to move. So when we reach the middle point, it has potential energy because it's at a height, and it has kinetic energy because it's still moving. And then once it reaches the bottom, right before it hits the ground. So let's drive this idea out of our heads that once it hits the floor, it's zero. No, we're going to pretend that idea doesn't exist. We're going to assume that it's the moment right as it hits the floor. Okay? So right when it hits the floor, there's no potential energy because there's no height. Now, when it reaches right before the bottom, that's when it moves at its fastest. So all we have here is kinetic energy only. So notice how there's a shift from potential energy going down as kinetic energy goes up because we're getting faster and faster. So there's a shift from one form to the other. And so, but this total energy stays the same. So whatever energy you start out with at the top stays constant throughout. So if pretend you start out with 25 joules, you carry that 25 joules throughout the entire way through because the total energy doesn't change here. So remember that when you're at the top, you have max potential energy. When you're at the bottom, you have max kinetic energy. And if you're somewhere in between, you have a mix of potential and kinetic energy. Okay? And if you would like to use this equation, Kp equals kPaf. This is the conservation of energy equation, where you look at the total energy before, which is equal to the total energy after. And this can be used especially when figuring out different aspects of the object as it goes from one to the other, top to bottom or bottom to top. Okay, Kp equals kPaf. Now, internal energy, and this is only considered when sound and friction are involved. So sometimes you'll see in problems where at the end of it it says neglect friction. You'll see this written in problems. That's when you forget internal energy. But if they don't mention this part, neglect friction, that's when you need to take into account internal energy. If you think about heat, friction, sound, whatever. So the sum of kinetic and potential energy is called total mechanical energy. Okay? Now if this is involved, then we have to look at this equation. Okay? So if we think of objects, if you're doing work to make it move, and you give some of that, you give all that energy, if you give 1,000 joules and part of it's used for kinetic energy, then the other part becomes either potential or internal energy. If we think about a bouncing ball as our example, ideally it should bounce back to the same height you dropped it. However, it doesn't. And that's because you hear a sound and there's air resistance, so internal energy comes into play here. And that's where that lost energy, in quotes, comes into play. Alright, so internal energy only matters when sound and friction are involved. So look for those keywords. Friction, frictionless, that'll help you keep track of whether or not to use internal energy or not. And that is the end of this particular content video. Now we're going to go forward with part 3 about springs. Okay?